Hi, my name is Rahim. I'm the product line manager for Semiconductor's isolation products. And with me is John Constantino, the director of isolation products. Today we're going to present digital isolators or optocoupler, the advantages and disadvantages of each isolation technology. So today there's many different choices for technologies for isolation devices. We're going to cover the different technologies, their strengths and weaknesses, and help guide you through how to choose the right technology for you and your customer. Just a quick note on isolation for those that are not familiar. We're talking about galvanic isolation or electrical isolation, where there's high voltage isolation between two different circuits. The purpose of the isolation devices is to provide safety for the end user and protection between the low voltage and high voltage circuits. Isolation devices also provide the benefits of filtering common mode noises and eliminating ground loops. Optically isolated devices have been in the market and available for over 50 years. And in the last 10 years, we've seen the introduction and growth of digitally isolated devices. Those are implemented as on-chip capacitors or inductors, and ON has just been introduced the Digi-Max technology, which is an off-chip capacitive isolation. Before we get into the technology, I wanted to review the market conditions for isolation. Today, the market is still vastly the optical solution, but we're seeing a lot of growth in digital to the point where it'll be about a third of the market by 2025. Some of the growth in digital is from applications like automotive electrification, which are primarily using digital solutions. And we're also seeing some transition from optocouplers to digital in what we call logic-to-logic devices. On the bottom right, you can see that there's a lot of growth in gate drivers in general in automotive for the powertrain of electric and hybrid electric vehicles. And this is causing a large growth in digitally isolated gate drivers in the market. So the different techniques to create the isolation are optical, capacitive, and magnetic. Optical uses an LED emitter and detector across a physical gap. This has been around, as I mentioned before, for over 50 years. However, some of the limitations is that the LEDs degrade over time and performance changes quite a bit over temperature. Also, the speeds are limited in optocouplers, peaking at about 25 megabits. And in some applications where we see high channel counts, sometimes you see 6 or 10 or even 20 different data lines, optocouplers are limited to 1 or 2 channel devices, and when you have a high channel count, it can become quite expensive and require a lot of board space. For capacitive, this is where we see the on-chip and on Digi-Max off-chip technologies. These create a capacitor in the device, either through an oxide insulator or in the Digi-Max case by adding a ceramic substrate between the capacitors. We're also seeing magnetic solutions where a coil is integrated as part of the chip and provides the communication across a polyimide layer. At this time, I'm going to turn it over to John to talk more about the different technologies.
Okay, thank you, Guy. As Guy mentioned, there are multiple technologies that can be used to implement galvanic isolation. The optocoupler is the tried and true technology that's been around for decades. This technology uses light to transmit information across the isolation barrier. The primary benefits are the safety reliability for high voltage applications and the options for low cost implementation for applications where you just need a single channel, simple isolator. The optocoupler can't be beat in terms of price. Some of the primary weaknesses are the LED degradation that happens over time and temperature variations as well. The target markets are basically you can find optocouplers in every market segment, but the main applications where you'll find them are industrial automation, in white goods, power supplies, and solar inverters. Semiconductor has a broad portfolio of optocouplers from phototransistors to high-speed optocouplers, which high-speed in terms of optical technology means up to about 25 megabits per second data rates. Optotriac drivers and gate drive optocouplers, which are MOSFET and IGBT drivers. For on-chip galvanic isolation, there are two technologies. There's on-chip inductive or on-chip capacitive. This technology offers the highest speed and consistent performance over temperature. The primary weaknesses are the thin isolation barrier, which I'll talk about in a later slide, as well as the isolation structures not being protected from EOS or ESD. That'll also be shown in a video later in this presentation. The target markets are mostly automotive, PTC heaters, onboard charging and traction inverters, as well as industrial automation. Semiconductor offers single and dual channel gate drive digital isolators, as well as smart and advanced gate drive digital isolators. For the Digi-Max technology, this is using a ceramic off-chip capacitor, and I've got a slide that shows more detail later. The primary benefits are reliability and safety, high speed, and consistent performance. So basically, this technology combines the high voltage safety reliability of the optocoupler using a thick insulating barrier inside the package with those electrical performance benefits that digital isolators offer. Primary weaknesses are cost and power consumption. The ceramic isolator technology is a little bit more expensive to implement, and the capacitors are large, so the power consumption is slightly higher than compared to the on-chip version. Target markets are industrial automation, solar inverters, and the same automotive applications that on-chip isolators are found in. The Digi-Max is currently available in 2-channel bi-directional logic-to-logic. However, we'll be launching more products in this family, up to 6 channels and multiple channels communicating in each direction. Taking a closer look at a comparison between the different technologies, the life expectancy of the devices, typically for digital isolators, are 20-plus years. For optocouplers, it's listed at 10 years, mainly because of the LED degradation. However, this is well understood, and it's typically 1% to 2% per year. And with the average operating temperature and LED bias current, we can provide models to show the degradation trend for the devices, and this lifetime can be extended out with proper guard banding in the design of the optocoupler into the application. The distance for insulation is the thickness of the isolation barrier inside the package, so the spacing between the primary and secondary conductive points. For the optocoupler, it's 400 micrometers or greater typically, and for the Digi-Max, it's 500 micrometers or greater, where with the on-chip isolators, it's about 20 micrometers. What this means is the optocoupler and the Digi-Max provide intrinsic isolation safety. The working voltage of the part is the operating voltage that the part can withstand across the isolation barrier consistently throughout the lifetime operation of the device. With 3,000 volts per millimeter breakdown in air as the laws of physics, with a 0.5 millimeter distance for insulation, that would guarantee 1,500 volt minimum working voltage, even if there is no benefit provided by the insulating materials between those conductive points. With the on-chip solutions and the 20 micrometers, it guarantees only about 70 volts of intrinsic working voltage. Any voltage above that, up to the rating, maximum working voltage rating of the part, which is typically several hundred volts to over 1,000 volts, that has to be guaranteed by the integrity of the insulating material between those conductive points inside the package. The IEC standard EN 60950, it's recently been replaced with a new standard, an updated standard. However, the original standard had a 0.4 millimeter distance through insulation requirement. There was testing options that were derived to work around that requirement to allow digital isolators into the market. However, our optocouplers and our Digi-Max continue to adhere to the original intent of that standard and does not require test around options to get around that original requirement. In terms of EMI and EMC, optocouplers are relatively simple. They're too slow to respond to extremely fast transients and EMI in the applications, and they use light transmission, so radiation is typically not an issue as well. However, with the digital isolator solutions, more care has to be taken, both from our standpoint as suppliers designing the ICs using proper filtering techniques and minimizing the radiated energy, as well as on the customer side with the board layout to make sure that you pass these EMI and EMC requirements. In terms of safety standards, the optocouplers and digital isolators are all tested and certified under the UL 1577 standard. For the European standards, the optocoupler follows the IEC 60747 standard, which is based on a partial discharge model, while the digital isolators are currently certified under BDE 0884, and soon they're coming out with a new IEC standard that digital isolators will fall under. And these are based on time-dependent dielectric breakdown models where we run tests for many thousands of hours at different voltage levels, create a logarithmic plot, and that generates the lifetime at various voltage level model. So looking closer at the capacitive on-chip and off-chip solutions, the Digi-Max, as I mentioned, utilizes a ceramic substrate that's off-chip. We call it off-chip isolation because it's not embedded in the transmit and receive ICs that are providing the RF signal communication. How we do this is we have the ceramic substrate, which is this green area. We deposit metal on both sides of the ceramic, which forms a capacitor. This is 0.5 millimeters thick. That's where we get the 0.5 millimeter distance for insulation. We have a transmission line that carries the signal from one side of the device to the other. And then we have a via that carries the signal back through the ceramic substrate. So the distance through insulation is 0.5 millimeters because that's the smallest distance between primary and secondary side contact points. We also have another primary to secondary contact spacing, which is along the surface of this ceramic substrate, and this is 0.8 millimeters minimum in our Digi-Max technology. We implement this through pairs of capacitors. So in our device, we have two sets of capacitors, one for each direction of communication across the isolation boundary. And we use two sets of capacitors for differential mode communication. This allows us to cancel common mode noise and provide a more reliable communication across the isolation barrier. With the on-chip solution, the capacitors are formed within the semiconductor silicon process using a thick SiO2 or silicon oxide process. And this is, again, about 10 micrometers thick on each die, and they typically have two capacitors in series. So one of the challenges is if you have an electrical overstress event, you have to be careful not to exceed the power ratings of the IC, because if you get some EOS damage or carbonization on the die surface or within the die, it could impact these isolation structures and degrade the isolation performance. And we have a video that will show that shortly. With the Digi-Max solution, the capacitors are off-chip, so even if the die is damaged, you'll still have reliable safety isolation because the isolation structures are protected. Looking at the working principles of the ceramic digital isolator, the electrical and the modulation scheme is similar to the on-chip isolators where we use on-off keying. What that means is when you have a input signal that is low, the modulation is not passed through the capacitors and the output stays low. When the input goes high, the capacitor is modulated and the signal is transferred across the isolation barrier, and you end up with a change in logic states on the output. This is showing positive logic, but we also have the opportunity to do inverting logic as well. And this is called an on-off keying technique. And again, it's common in the industry. One thing that's unique, though, about our ceramic digital isolator is the fact that we multiplex the data across the capacitors when we have multiple channels communicating in one direction. This is because the capacitors are large, so we don't have the space inside the package to dedicate a capacitor for each channel of data inside the package. What this shows here is the internal clock in our part. Depending on the number of channels, you divide that clock cycle by the number of channels communicating in one direction. In this example, we have 4 channels communicating in one direction, so we're using for each channel 1 clock cycle out of every 4 to communicate the data. And we show 2 cases here. One case where the input or the data coming in arrives just after the clock signal. So it doesn't get read until the next clock cycle for that channel, say channel 1 in this example, and therefore the output doesn't switch until that clock cycle is complete and that delay is overcome. So basically you can consider this transmitting within 2 clock cycles. In case number 2, we show the data coming in just prior to the clock signal, so it gets read on this first clock cycle, and then the output switches at the end of that first clock cycle. If you're looking at this on an oscilloscope, it might look like jitter, but it's not traditional jitter, which is random noise. This is more of a bimodal propagation delay, where you have either 1 clock cycle or 2 clock cycles to receive the data on the output, depending on the timing of when the data arrives. And this is because of our Manchester encoding technique and the fact that we multiplex across the capacitor. There is an option to offer a clock pin so that you can use that to feed in your external clock signal and synchronize the data. That eliminates that chance for the data to arrive after the sampling occurs. And then you can reduce the pulse width distortion to about 1 or 2 nanoseconds. Looking at the CMTI performance, this is looking at the negative pulse. So this is the positive to negative slope, and then the negative to positive slope in this example. Looking at common mode high and common mode low, I take the worst case specification for the rating because they're different for each device between CMH and CML. Looking at the Digi-Max, it's passing our maximum test capability, which is 158 kV for the positive, for the negative going slope, and then 157 for the positive going slope at 3,000 volts common mode voltage. For the on-semiconductor digital isolator, which is the on-chip version, it's passing greater than 150,000 volts per microsecond at 1,500 volts. For the competitor devices, some of them pass at the maximum capability of our tester, while others are failing, and we're showing ones here that are failing at about 63 kV and 1,000 volts common mode for the negative going pulse, and for positive going at 120 kV per microsecond at 2,400 volts. The optocouplers typically start to fail at about 70,000 volts per microsecond at 1,200 volt common mode voltage. So looking at the technology recommendations, these are the decision factors for each technology, the things to consider when you're looking at implementing galvanic isolation. For the optocoupler, one of the big benefits is you don't have to have, for the simple devices, isolated power supplies on each side of the package. And that can come in handy where you just have an LED, you just have to supply the input signal to power up the LED and the ground. For single and dual channel applications, optocouplers make a lot of sense. When you go above 2 channels, then you have to use multiple single or dual channel optocouplers, and then the cost savings start to decline versus digital isolation. So again, for single channel low performance applications, the optocoupler is the most cost-effective solution. Also for direct interface to AC mains, so if you're driving a solenoid or a motor off the AC mains, the triac drivers are a good solution because you typically have 600 to 800 volt blocking voltage requirements to be able to stand that off and control the gate of a SCR or power triac. And the digital isolator processes are typically not compatible to combine a high-frequency gigahertz RF carrier circuitry with a high-voltage 800-volt or 1,000-volt power discrete devices. Also, they easily meet the EMC requirements, so it simplifies the board design. For digital isolation, a lot of the benefits I'll just combine for Digi-Max and digital isolation in terms of the electrical performance. You have the long life expectancy, actually greater than 20 years. Grade 1 automotive devices, there's a lot of options out in the market to choose from. With optocouplers, the selection is quite limited for automotive-grade optocouplers. We at ON do not offer automotive-grade optocouplers, and most of the suppliers in the market do not. That's mainly because of the concerns about the LED in those high voltage and rigid environments. It's best to use the digital isolation in those applications. For high channel count, digital isolators become cost effective when you can have up to 6 channels in one package. And the bi-directional communication, there are many more logic-to-logic devices available in the market in digital isolation compared to optocoupler technology. And of course, the consistent performance over temperature as well. The decision factors for the Digi-Max are, again, the same as the digital isolation, except when you have high voltage safety reliability concerns. A lot of customers are still using optocouplers that may want to go to digital isolation, but have concerns about moving to a thin film insulator material. And now I would like to show a video I referenced earlier that shows the benefits of the off-chip Digi-Max isolation in the presence of ESD or electrical overstress conditions.
Hello, I'm John Constantino, Director for the Isolation Business Unit at ON Semiconductor. Today I'm pleased to introduce ON's patented Digi-Max digital isolator. This product is not the typical digital isolator you're used to seeing offered in the market. Our patented construction with ceramic substrate delivers off-chip capacitive isolation with a thick dielectric insulating barrier. This unique construction allows us to offer the high insulation reliability of optocouplers combined with the high-speed, stable high-temperature performance of on-chip digital isolation. The capacitors are formed by placing metal plates on both sides of the dielectric material with a transmission network to communicate the signal across the isolation boundary. This results in a 0.5 millimeter distance through insulation, which guarantees by design a 1500 volt isolation working voltage. The devices being offered in this construction are high-speed logic-to-logic digital isolators housed in a 16-pin wide-body package. This package guarantees 8 millimeters creepage and clearance spacings. Devices offered range from 2 to 6 channels in unidirectional or bidirectional communication configurations. Now we will demonstrate the reliability of Digi-Max off-chip isolation. In this experiment, we connect a power supply between the VDD and ground pins of the devices. The current limit is set at 600 milliamps and the voltage is ramped to the breakdown limits. As the power increases, the device heats up and then fails. This simulates an electrical overstress event that can occur in applications. Here is the resulting damage on the ICs. On the left is the ON Semiconductor Digi-Max isolator. On the right is the competitor's on-chip isolator. Both ICs are damaged. The parts were tested prior to decapsulation for the isolation specification VISO at 5,000 volts for 60 seconds. Here we see the competitor part fails at 2.76 kilovolts following the EOS event. Now we test the Digi-Max isolator, which is still passing 5,000 volts after 60 seconds, even after it had been damaged by electrical overstress. This experiment shows that the isolation performance of the Digi-Max isolator remains intact even after the EOS event, while the competitor part has degraded. Similar to optocouplers, in the Digi-Max technology, if the IC is damaged, the device may no longer function electrically, but the off-chip insulating materials are protected and continue to provide reliable isolation. This fail-safe operation is ideal for safety isolation in high voltage applications. To learn more about the Digi-Max isolators, please visit us online at www.onsemi.com. Thank you.
At this time, we want to review some block diagrams to show how each technology is being utilized in these systems. We like to start with three-phase motor control. This is to show how all three technologies fit into these applications. Here we're seeing optical-based IGBT gate drivers to drive the motor. This is still very popular in industrial robotics and automation. There's also a digital isolator that provides the feedback data from the high voltage side of the motor to the low voltage circuitry from the control unit. Here you can see how for automotive application, we've replaced the optically based isolators with digital isolators and with standalone gate drivers. And finally, now we're showing replacing that with digitally isolated gate drivers. And so we're still seeing all three applications, all three technologies being used in this application. In this slide, you can see a block diagram for network communications where multiple optocouplers are used for data communication. You can see on the left side, we're still highlighting the optocoupler. As mentioned before, single channel, low performance can still be done with optocouplers. Whereas on the right side, where there's multiple channels, it might be more economical to replace 4 single channel optocouplers with one Digi-Max 4-channel device or another logic-to-logic digital isolator, or two channel optocouplers with a single 4-channel digital isolator. Another automotive application that is very popular for isolation products is the PTC heaters. You can see that in this diagram, we're showing multiple devices across different technologies. There's a digital isolator that allows multiple channel communication from the microcontroller to some of the sub-circuits, an isolated gate driver to control the IGBT device that turns on to warm up the PTC heater, and additional digital isolator and non-isolated gate drivers in this application. As John mentioned earlier, triac optocouplers are not easily replaceable with digital devices, and so in many white goods or industrial type of systems that use solenoids, we still see a lot of triac optocouplers. We can also see isolated gate drivers, either optical or digital, to drive the motor portion of this washing machine, as well as optocouplers for a simplified power supply feedback loop. Where we see a lot of conversion from optocouplers to digital isolators are in these type of analog input modules, or as well as digital input modules or mixed signal modules. This is where previously you would have multiple optocouplers to carry the data across the isolation boundary. Here, there's one digital isolator to control the mux switching and a digital isolator to provide bidirectional data across the SPI bus to control and read the values of the analog to digital converter. And finally, we're also showing a switch mode power supply. This is where, again, we see a lot of optocouplers still in the market, as a single channel low performance solution is the best for this application. As a supplier of both, as a supplier of optocouplers and digital isolators, we're able to show that there's not one solution that's right for all applications. Sometimes a simple optocoupler is all that's needed, or sometimes a more complex digital isolator or even an integrated isolator with gate driver is the right product for that application. If you'd like to find out more about our optocouplers, digital isolators, and isolated gate drivers, you can visit the links below or go to www.onsemi.com. On behalf of John and myself, I'd like to thank you for your time for this presentation. Thank you.